now given any CNF, you can just think about its clauses and then apply the single rule RPL, resolution for propositional logic, and your aim is to show that it is unsatisfiable or not. Now, if it is unsatisfiable, you are confident that you will be able to derive bottom. Why you are confident?
Removing the redundant terms, not P and or not P or not P or P which is anyway equal to 1 and all. So those terms don't actually contribute to the satisfiability of the entire CNF. So therefore, even if you neglect it, at the end if there will be other terms which are clearly not going to lead to satisfiability or rather lead to unsatisfiability. Therefore, we can safely say that the entire CNF is unsatisfiable.
Suppose you are not able to derive bottom, can you say it is satisfiable? That is what I mean by confidence. Both the ways you should be able to tell it.
We can say satisfiable, we can't tell. We can say it's satisfiable, but we may not be able to tell if it's valid.
See, I can proceed only one step. I say I am not able to derive bottom, therefore it is satisfiable, whereas it can be unsatisfiable. Do you see the problem? It is like whether this problem is solvable or whether I can solve it. If you are not able to solve it, you say it is not solvable. That is wrong. Okay? So, what you need is a mechanical procedure, whether mechanically something can be done, not only whether I can do it, but anyone. Fine. So, how to mechanize it? Resolution procedure. Maybe something like we will try to derive everything possible, very crude way, but let us see, there should exist some mechanical procedure first, then you can modify and make it better. Fine. So, suppose we start with one example. Say I have these clauses P or Q, say not P or Q, and say another not P or not Q. These are the three clauses given. Now, you want to find out by resolution what is happening. Okay. So, usually what you will do, you proceed by taking these two, let us say. So, you get Q from this by resolution, taking the biform variable as P. Okay. Similarly, from this you would take what? Again P. So, you get Q or not Q, or you would have taken Q as a biform variable and get P or not P, that adds no information. Okay. From these two, Q and not Q can be taken. So, you get not P, then well I am not able to derive anything, that is my position. You also say you do not have any way to go on, right, but it is not possible. How to show it? Well, it is a simple example. Here we can explore everything and say nothing is possible, but finally you will be giving one interpretation, right, which is satisfying. So, you have P and Q, these two are there. So, try to satisfy them. So, I take Q to be 1, P to be 0, these two are satisfied, and now try verifying everything, but we have to go back to semantics, that is what it is. Fine. Here we have the confidence. If I am not able to go for the bottom, then I can show that it is satisfiable some way, but by using semantics again. Fine. To make it mechanical, what we do is just look at what we are doing. We have started with a set of clauses CNF, let us say A. Then from this CNF we go to taking resolvents. So, instead of choosing some, let us take resolvents of all possible clauses, all possible pairs of clauses. Okay. Then what do we do next? Take resolvent of resolvents, right, and continue. Finally, I should say that it will terminate somewhere. Termination means it will simply repeat whatever I have already derived, it will not add anything new. So, I have to guarantee that it will happen. Fine. Once this happens, I just check whether bottom is there or not. If bottom is there, it is unsatisfiable. If bottom is not there, that is the problem. It may be satisfiable. That is what I am guessing now. It will be proved when I give one interpretation, which is a model of the CNF, maybe taking hint from all those unit clauses I have derived. Fine. But what we want really is, if I have reached that stage where I cannot add a new clause and I see that bottom is not derived, it should be satisfiable, right. Then you say that resolution is a complete method, you do not need any other rules, only a single rule RPL is enough, otherwise some other rule might be required. Fine. Is the position clear what we are going to discuss? So, this is what we want to do first. First formalize this procedure as resolvents, taking resolvents of resolvents and so on. Fine. So, suppose A is a CNF. Okay. Then what we are going to do is take resolvents of A, put them together, but then with the resolvents you may need another clause of A to be resolved, not only resolvents of resolvents, but original also. Fine. So, what we do is, we let us say R0 of A equal to A, right, and then I define Rn plus 1 of A to be Rn of A union resolvents inside Rn of A. So, that will be resolvents of A B with some biform variable P, such that A and B are in Rn A and P is a biform variable or biform literal. That is what we are going to do. Okay. Then finally, we would like to say that I have achieved everything, no more to go. So, I say it is the resolvent closure, which is simply union of all these. So, theoretically it looks like this. I take all possible resolvents up to any stage whatsoever. Fine. So, if you take R0A, you have not used resolution at all, it is your original CNF. So, once you take, that means you have taken resolvents on A, twice you take, so that means R2A. So, there you have done resolvents of resolvents, not only that, including resolvent possible along with the original CNF also, right. No, you have just defined it, it exists. What we mean is whether R star A will terminate, whether this process will give me R star A, but R star A as we have defined, it exists mathematically. We are not telling it is some RMA, we are telling it is union of all those things, right. So, what you want is to show that R star A equal to RMA for some M, right, and that should be possible when, say Rm of A equal to Rm plus 1 of A. So, that should be the R star A, because each Rm plus 1 contains Rm by definition, it is increasing. Okay. So, once Rm equal to Rm plus 1, that should be equal to R star. Is that clear? And what is the guarantee that there is one M such that Rm equal to Rm plus 1? Yeah, that should be guaranteed.
Number of iterations is finite. That we are using
Some finiteness somewhere. So, the finiteness comes from the CNF itself. It is a CNF, so it has some length. The number of propositional variables in it occurring in it is finite. Then the number of clauses that can be generated from those propositional variables is also finite. Is it clear? Suppose I have P and Q. So, how many clauses you can generate from it? Well, from P, how many clauses you can generate? Suppose I have P, a single variable, how many clauses you can derive from this? 1? Well, there can be 4. No? Well, 1 is bottom, trivially, another is P, another is not P, another is P or not P, all possible, we are taking all possible things. Is that okay? Fine. See, there is, suppose there are n propositional variables. So, there are 2 n literals, for each P there is a not P. So, there are 2 n literals. Now, these 2 n literals can give rise to how many rows in the truth table, if you view that way? Yes? Huh? Well, you want to form a clause using these 2 n literals. So, let us take a clause has now 2 n vacancies, each one can be filled with something, right. Let us make their places. First one is for P 1, next is for P 2, next is for P 3, and nth one is for P n. Next one is for not P 1, next one is for not P 2, and so on. Fine. Now, if I give 1 there, that means it is there. If I give 0 there, it is not there in the clause, right. So, one of the literals can be in a clause or may not be in a clause. So, there are 2 possibilities. So, 2 to the power 2 n maximum, is that right? Okay. So, maximum these many clauses can be formed out of these literals, but then there will be some trivial clauses which we are not really taking. For example, this one we may not like to have it, does not matter whether it is there or not in a CNF, fine. So, that reduces to 2 to the power 3 n cases, okay. Sorry, 3 to the power n, not 2 to the power 2 n, which is 4 to the power n, we will have only 3 to the power n. See, the thing is, if you take a clause, either P is there or not P is there or nobody is there, right. So, there are 3 possibilities always, fine. So, you can get only 3 to the power n, even including bottom we are interested in. So, we are not deleting it, fine. Anyway, whatever it is, there are only finite number of clauses possible, okay. Now, when you go for taking the inductively these sets, resolvents of resolvents and so on, so some stage all the clauses will be over, no further additions can come, because there is finite. Therefore, R star A will be equal to R m of some A, right. 3 to the power n it is coming now, finally maximum possible, all possible, they may not be interesting to us, right. Okay. So, that is finite anyway. So, once it is finite, we say that R star A is equal to R m A, which is equal to R m plus 1 of A for some m. What happens here? We have gone up to stage 2 and stopped there, fine. So, it should terminate in R 2 or R 1, R 1 equal to R 2. It is really stage 1, no? This it is not stage 2, it is 1 itself. So, R 1 A should be equal to R 2 A should be equal to R star A, that is our guess. Let us verify it. So, I have now A equal to P R Q, not P R Q, not P R not Q. So, R of A will be equal to all those things, and there might be more because of resolvents. So, we add the resolvents. Now, starting from this we take the next one. So, we get one resolvent by taking P as the biform variable, we get Q, there is no other way possible. Now, 1 with 3 gives again with P I get Q or not Q, with Q I get P or not P. They are not interesting ones, you can delete them, but still let us go on keeping what we are getting here. These are the two possibilities. Then with second and third, second and first we have done. So, second and third, that is from A we are taking. Let us look at this place rather. So, second and third, q is only the biform variable, we get not p. That is all, starting from A, no more is possible. Fine. Now, at this stage you can delete them, but even if you keep, it does not matter. Let us go on keeping, mechanically we are doing it. Okay. Then let us go for R2 of A. So, this is A equal to R0 A also in our notation. Now, it will start from R1 A as it is. So, we start with P or Q, not P or Q, not P or not Q, Q, Q or not Q, P or not P, not P. Then start taking resolvents, all possible resolvents. So, first P or Q with not P or Q we had taken earlier. So, there is no need up to this place with the first class. So, second one not possible, third one possible with not Q and Q, that goes. So, that gives me P or Q again, right? This Q not Q. So, I get P or Q. Okay. Next this one with not P. So, these two go, I get P or Q. Next with not P, same thing happens, or Q is coming, Q is already there. Okay. So, with first nothing happens. Similarly with second we have to verify, it is tedious, but let us do it. So, second with third we have already done it. So, second with Q not possible, second with Q or not Q, not Q we can have. So, we get not P or Q. Okay. Is it there somewhere? Not P or Q, right? Then not P or Q with P or not P, not possible, with not P, not possible. It is here already. Okay. Next what we do with not P or not Q. So, with Q that gives not P, it is here. With this Q and not Q goes, so I get not P or not Q, which is that itself, and this with P gives not P or not Q, that is again there, not P, not possible. Fine. Now, with Q, these two will give Q, these two not possible, these two not possible. Then Q or not Q with this not possible, this with not P, not possible. Then these two, so not P and P goes, I get not P, that is already there, that is all, right. So, this is equal to R1 of A. So, that is our verification that R star A should be equal to R1 A. Fine. So, it terminates there. Now, that termination is guaranteed, our procedure says if bottom is at all generated, it is unsatisfiable. If bottom is not generated in R star A, it is not unsatisfiable, it has to be satisfiable. Fine. So, that is our guess now. Guess is bottom belongs to R star A if and only if R star A is unsatisfiable. Fine. But this is only a guess till now. Well, one side of it you can finish quickly. If bottom belongs to R star of A, then R star is unsatisfiable. That also gives you A is unsatisfiable, because A is a subset of R star A. Does that? Just a subset may not give unsatisfiability, it gives satisfiability. but because it is resolvent closure R star of A. So, you have to do something more there, right, but that can be done because it is derived from it, because of the resolution principle. Any clause there is a consequence of A, that is the reason, fine. So, bottom is also a consequence of A, that is how A can be unsatisfiable. But what about the converse? If bottom is not at all generated, we must be able to show that R star A is satisfiable or A is satisfiable rather, we are interested in A, fine, this is what we want. So, for that we have to do some more work, it is not easy, we will be doing something starting from somewhere, you will not see where the connection, but slowly you will realize as we go along there is a connection. So, let us try it. So, for the starting point is coming from somewhere, we do not know. So, do not be getting afraid, fine. Now, the thing is A is a CNF, since it is a CNF there are only a finite number of propositional variables occurring in it. So, now we are going very systematically. If it is so, then we start from P0, go along, find how many are there, up to what stage the variables can be there, right. So, this is the starting point. So, suppose we enumerate all the propositional variables, they are already enumerated, right. If you look at our syntax, they are already enumerated, you have started with P0, P1, P2 and so on. So, let us write that, enumerate all propositional variables. As let us say P0, P1, P2 and so on, fine. So, let AM be the set of all clauses. So, remember clauses means disjunctive clauses here, we are not specifically writing it, in this context clauses means disjunctive clauses, set of all clauses formed or using the first m variables. So, the first m variables means 0 to m minus 1, that is from it uses from all this P0, P1 up to P m minus 1. Okay. Suppose we call it AM, all possible clauses you derive or you are able to form, not derive, using these variables P0 to P m minus 1. It is not necessary that all the variables have to be used, okay. Only 2 of them I can use, that is also a clause allowed. So, the other variables are absent there, that will be its interpretation, okay. So, in that case let us see what is A0. For example, A0 can be what it can be. So, all clauses you can form using variable P0, you may not use at all. So, bottom it is empty, then you can have P0, you may have not P0, you may have both, that is all, okay, fine. Similarly, next one P1, so you can have P0, you can have P1 first of course bottom, then you can have not P0, you can have not P1, you can have P0 or not P0, you can have P0 or P1, P0 or not P1 and so on, all those you can have, fine. A1, yeah. What is the question?
So, you said AM is the set of all clauses formed by the first m variables. So, if m is 0, then we are not using any variables.
First m variables from the list. So, if you take first 3, it will be P0, P1, P2.
But if m is 0, it will be first 0 variables.
No, no, first variable is P0, right, in that sense, not m cannot be 0 here, m is 1 onwards, because you are counting, na? You are counting them. So, first second there is no 0th, okay. So, what we write is, so let us say Okay, you want the notation to be different, huh? Okay. In that case, what we do, all clauses formed from the set, this, that is all, huh? Formed using variables from, that is all. Okay. Is that clear now? Let us forget about that first, second and so on. That may be confusing. So, we will write, let M be the set of all clauses formed using variables from this set, P0 to Pm minus 1. Okay. But M cannot be 0, that is the problem. If you take M 0, this will become minus 1, so this is empty again, because 0 is there and we have to write A 0. Okay, you start M from 1, but M, if M is 0, we want P0 to be there. Okay. Do you see? So, if you want, you do not allow M to be 0, start from A1 itself. In this notation, it will be A1, there is no A0. Okay. That is fine, we continue with that, does not matter. If you prefer this, let us continue with that. A1 equal to this. So, now when you write this, it means M should be greater than or equal to 1 for us. Okay. Right. Now, then A2 we will have P0, P1 both. Okay. Clear? Now, what we do first is, what we want to prove is box or bottom belongs to R star A and R star A is unsatisfiable. We want to equate both of them. Okay. So, instead of going to R star A directly, we will go to R star A intersection with AM, see what happens, then finally we will generalize. Okay. So, that is the procedure. Now, you see the connection, why we are starting with this, starting with the first M variables, then slowly we are increasing it, so that it will be amenable to induction. Fine. So, what we do is, if R star of A intersection with AM is satisfiable, then R star of A intersection with A M plus 1 is also satisfiable. This is what we will prove first. So, how do we proceed? Well, this is satisfiable. So, there is a model of it, but this is a set of clauses. So, there is a model for the set of clauses, it is a CNF of course. So, now in a set of clauses there is a model, it satisfies each of the clauses simultaneously, that is what it says. Okay. So, suppose I satisfies R star A intersection AM. Okay. So, what is the difference between AM and R star A intersection AM plus 1? So, all those clauses are here also, fine, plus there are some more clauses which are having the occurrence of the variable Pm, Pm plus 1, Pm, right. So, notation we have to be careful. So, now Pm was not there earlier in R star A intersection AM, possibly up to Pm minus 1 are there, Pm is the extra one. So, there can be some more clauses. Now, when you think of this interpretation I, it is not defined till now for the variable Pm, fine, but when you want to make a model for R star A intersection AM plus 1, you need to define some value for this Pm. Okay. So, we will extend this interpretation I to another interpretation taking care of this variable P m. Okay. So, now extend I to two interpretations as follows. What we do? Let us call them the J and J bar. They are extensions of I. So, they will be defined from the set P 0 to P m now. See, I was defined only up to P m minus 1. Now, P m we have to take care. So, there is a possibility of extending by assigning P m to 0 or P m to 1. That is why you are starting with two extensions. We do not know which one will work. Fine. So, let us say where J of say P k, they must be same as I up to m minus 1. So, they are same, that is what we are writing here, I of P k for 0 less than or equal to 1, k less than or equal to m minus 1, and J of P k equal to 0, J bar of P m, last one, P m equal to 1. These are the two extensions possible. Our contention is that which one of these will work for R star A intersection A m plus 1, we do not know. Fine. So, we proceed by proof by contradiction. We say suppose that R star A intersection A m plus 1 is unsatisfiable. Okay. So, suppose R star of A intersection A m plus 1 is unsatisfiable. If it is unsatisfiable, then neither J nor J bar is a model. Is that right? It does not have a model, and we have two here, J and J bar. So, neither of them is a model. Why neither of them is a model? It is a set of clauses. Some clause is not satisfied, right? That is why. So, that means J does not satisfy some clause, J bar does not satisfy some clause, may not be same. Fine. So, then there are clauses C, C bar in R star A intersection with A m plus 1 such that J of C equal to 0, also J bar of C bar equal to 0. Okay. Fine. They are not satisfied. So, they are assigned to 0. That is why this is not happening, this is not satisfiable. Now, we know that J of C equal to 0, J bar of C bar equal to 0. Now, look at P m. P m may be occurring in C or may not be occurring in C. Similarly, not P m as a literal may be occurring in C, may not be occurring in C, right. Now, can it happen that neither P m nor not P m occurs in C? Then both J and J bar will be like I, because they agree with I on R star A intersection A m. Fine. So, let us write it that form. If neither P m nor not P m occurs in C, then C belongs to R star A intersection A m. Okay. And J is equal to I on this set. Okay. So, J of C should be equal to I of C equal to 1, right, contradicting J of C equal to 0. Okay. So, what is our conclusion? At least one of them occurs, fine. Then at least one of PM or not PM is in C. So, we will not say occurs, it belongs to C. C is a set now, it is a clause, fine. This is what we mean, it is not really occurrence, it is really belongs to C or not. So, let us write it out, better write is in C as it is. Occurs means if not PM occurs, we may say PM also occurs, we do not mean that, we mean either PM belongs to it or not PM belongs to it, that way. So, if neither belongs, then there is a contradiction, therefore, at least one of them belongs. If neither belongs, then C has no occurrence of PM at all, then C belongs to R star A intersection AM. Okay. On that, I is a model, so I of C equal to 1, and I and J agree, so J of C will be equal to 1, but J of C equal to 0. Is that clear? Okay. I will repeat. See, this variable PM is not in R star A intersection AM, it is in AM plus 1, okay. But our notation may create problem, we have changed the notation, no? Have we changed the notation? PM occurs in AM or not in AM? AM plus 1 it occurs, or it occurs in AM, does not occur in AM plus 1, which one is correct? It occurs in AM plus 1, does it occur in AM or not? Does not, because AM only has P0 to PM minus 1, is that clear? Therefore, this PM does not occur here, once it does not occur in C, then C has to be in R star A intersection AM. C is in R star, okay, fine. Now, C has the variables from P0 to PM, but PM does not occur in C, therefore, all the variables of C are from P0 to PM minus 1, okay. Is that clear? So, C belongs to AM. Now, since C belongs to R star A, C belongs to AM, C belongs to R star A intersection AM. Is that step clear? So, once you accept C belongs to R star A intersection AM and I is a model of R star A intersection AM, I of C equal to 1. That is your assumption, I is a model of R star A intersection AM. So, I satisfies C, I of C equal to 1, but I and J agree on all the variables up to PM minus 1. So, J of C is also equal to 1, right, but J of C equal to 0, that is the contradiction. Therefore, at least one of PM or not PM belongs to C, fine. We go to the next stage. Can it happen that not PM belongs to C, that is PM does not belong to C? Let us see. If PM does not belong to C, then not PM belongs to C. Why? Because at least one of them occurs, at least one of them belongs to C. So, if PM does not belong to C, then not PM belongs to C. If not PM belongs to C, then what happens? Yeah, J bar or J
satisfies
G satisfies C. Why?
because J of PM is 0.
J of PM is 0. So, this gives j of not p m equal to 1. Okay. And what about others in C? That is satisfied by I. So, that is satisfied with j, fine. So, j satisfies C, but j does not satisfy C. Okay. Therefore, P m does not belong to C, does not happen. So, P m belongs to C, hence P m belongs to C. This is our conclusion now. If P m does not belong to C, then not P m belongs to C. If not P m belongs to C, then you can write C as D or not P m for some class D, right. Now, D or not P m, D or not P m. Now, let us find out J. J of P m is 0. So, J of not P m is 1. It is an OR clause. So, J of C has to be 1. Whatever value of D is, does not matter, even if empty, does not matter. Okay. So, now not P m, J of C has to be 1, but J of C is 0. That is the contradiction. Is that clear? Okay. So, this cannot happen, therefore, P m belongs to C. So, similarly, what happens for not P m? So, we get P m belongs to C. Similarly, not P m belongs to C bar. So, now you have to repeat really 2 stages argument. First start with if neither P m nor not P m is in C bar, that is a contradiction. Next you start with if not P m does not belong to C bar, okay, then J bar you have to concern with, not with J. J bar of not P m is 0, so therefore, J bar of P m is 1. Therefore, J bar of C bar will be 1, but J bar of C bar is 0, that is the contradiction. That is why not P m must be in C bar. Then we can write C equal to D or P m, C bar as D bar or not P m. Okay. Both of them belong to R star A intersection A m plus 1, fine. Now, take the resolution that gives you D or D bar. Okay. Now, D or D bar belongs to R star A intersection A m. Why? Because resolution completeness is there, you are taking resolution closure R star. So, this is in R star A and this is not in A m plus 1. Well, it is, but we can say it is in A m. A m is a subset of A m plus in that sense, fine. So, this belongs to R star A intersection A m, fine. Is that okay? Since it belongs to, I satisfies this, right. So, I of D may be equal to 1 or I of D bar may be equal to 1, because I satisfies this. I is a model of R star A intersection A m, okay. This belongs to that set. So, I is a model of this. Therefore, I of D equal to 1 or I of D bar equal to 1, one of this is has to happen. Now, if I of D equal to 1, then what happens? What about C? We can't say J of. Well, we have to take one more step. If I of D equal to 1, then J of D equal to 1, because I and J agree up to P m minus 1, right. So, this gives J of D equal to 1. Then we have J of C equal to 1, contradiction. but j of c equal to 0. Is it clear? If I of d bar equal to 1, then we say j bar of d bar is 1, because I and j bar agree up to p m minus 1. Okay. Then we conclude j bar of c bar equal to 1, that is also a contradiction. So, that is all, every case we are getting a contradiction, whatever way we proceed, right. Why the contradiction? Because Sulema is proved, fine. We are not explicitly constructing which one of them will work, but say that one of them has to, it can be unsatisfiable, that is what it says. So, let us take the second step. So, it says though we are not proving for R star A directly, for R star A intersection A n we can do something. Similar thing we wanted for R star A. Here we show that it is for a subset, not for the whole R star A. If box is not generated up to nth stage, then we can say that is satisfiable. It is not exactly nth stage, but nth variables, including up to n minus 1, p n minus 1. That is what we are telling. Okay. It can be up to many stages, all stages even. In fact, more and more stages you go, less and less variable can come, right. It can be on the opposite side. Okay. Let us see how do we prove it. So, suppose, but how do we prove this? It does not look straightforward. Let us prove it by induction. Okay, induction on n, fine. So, first we can take n equal to 1. In that case, let us verify, if box does not belong to this, then R star A intersection A 1 is satisfiable. This is what we have to verify. Okay. Then what can be R star A intersection A 1? It depends on A, of course, what this A is, but does not matter. Let us find out A 1 itself. Okay. A 1 is there, but R star A intersection A 1 does not contain bottom, right. So, R star A intersection A 1 can have anything, but not this, right. It can contain other things, okay. And it can be a subset of this, it is intersection. So, it can be a subset of this, any subset of this. So, now whatever subset you take, it is satisfiable. The bottom does not belong to it, whatever subset of this set you take, that is satisfiable. Let us check. Can P0 not P0 be there? Both? If both are there, then by resolution bottom will be there. That is the only case you have to consider, right. But it is R star A you are taking, not only A1, you are taking R star A. So, resolvents are also there. Now, if both P0 and not P0 are there, then bottom also will be there, that is not permissible. Therefore, both P0 and not P0 are not there. If not there, then you consider all the subsets possible. One is P0, another is not P0 singletons, another is singleton P0 or not P0, then other twos or two combinations, all of them are satisfiable, right. So, basis case is over, done. Then for the induction step, so induction step, our assumption is, let us write it as induction hypothesis. This says if box does not belong to if bottom does not belong to R star A intersection A M, then R star A intersection A M is satisfiable. This is our assumption. Now, you want to prove if box does not belong to R star A intersection A M plus 1, then R star A intersection A M plus 1 is satisfiable. Fine. For M plus 1 we want to prove. So, you have to start with this if one. So, let this happen that empty clause does not belong to R star A intersection A M plus 1. We want to show R star A intersection A M plus 1 is satisfiable. This is what we want to show. So, how do we show that? Yeah. See, this R star A intersection A M plus 1 is a superset of R star A intersection A M. It contains that. Therefore, if box does not belong to this bigger set, box does bottom does not belong to R star A intersection A M. Okay. So, now you see that bottom does not belong to R star A intersection A M. Reason is R star A intersection A M is a subset of R star A intersection A M plus 1. Fine. So, bottom does not belong to it. If bottom does not belong to it, by induction hypothesis this set is satisfiable. We will just finish. Then by lemma 1 R star A intersection A M plus 1 is satisfiable. Okay, over. That is what we wanted. It is simple step. Once you finished lemma 1, it is simple. Okay. So, all that we have done is we have done it up to A n. If bottom does not belong to R star A intersection A n, then this is satisfiable. This we have to generalize to R star A directly now, not basing on this A n. Okay.